So hi everyone, welcome to lab 3 of STAT115 and 215. I'm Gigi Ken, you can call me Scarlett. I'm going to be your TA for homework 2. I have 2 announcements to make before we get into our lab materials. So first, homework 2 is already out and it's due February 21st, which is one week, like next Sunday, 2 weeks from now, by midnight. And everyone should already have a Canada account to proceed with your little homework. So here's some outline for our today's material. Today we're going to mostly focus on the first part of homework 2. And the next week, we're going to talk about machine learning and modeling accuracy comparison, which is the second part of the homework 2. So today we're going to cover PCA, hierarchical clustering, batch removal, DSIG2, K-means, David, and GC. These are the packages you will need to install to run this R Markdown file. So you can use either the install the packages or the About C manager install to install this. So first, we're going to talk about the PCA. So often it's not helpful or informative to only look at all the variables in the data set for correlation or covariance. A preferable approach is to derive new variables from the original variable that preserves most of the information given by their variances. Principal component analysis is a widely used and popular statistical method for reducing data with many dimensions. By projecting the data with fewer dimensions, use the linear combination of the variables known as the PCs. The new projected variables are uncorrelated with each other and are ordered so that the first few components retain most of the variation present in the original variables. Thus, PCA is also useful in situations where the independent variables are correlated with each other and can be employed in exploratory data analysis or for making predictive models. So the PCA, the PCs are like the linear combination of variables, but it's not the best ones, just the ones that describe the largest variation. In our case of studying the gene expression, we can use we can reduce our dimensions from very high dimensional to a lower dimensional matrix. So here's a little example of showing how the PCA works. So first, we're abandoning these 2 axes, which originally defines these dots right here. We take this new 2 dimensions. So first, we can see the PCA1 is the axis where the dots can project to and have the largest variance. And there are 2 observations for the second PC. The first one is we can see the second PC is if the dots project to the second PC is less variable than the first one, and the second one is we can see that the PC2 is orthogonal to PC1. So that means PC2 is uncorrelated to PC1. So here is just a little example of the PCA, it's a PCA analysis. So we're using one of the data set from online database, and it contains 23 individuals with 10 variables. If you're using a local directory file, data set or something, you can use the read.cvs and the read.table to read your data. Here, I'm just using this because it's just online data. And we're using the PRCOP to do the PCA. Here, I'm just doing some of this calculation to make my plots in a better sense. So from this graph, we can see that our first PC already covers 41.2 variation, and the second one covers 18.4, third one covers 12.4% of the variation, and so far so forth. So we can confidently say that the first PC already covers most of the variation within the data set. So we don't need to we don't really need to care about the rest of them. Maybe the first one, but not so further after the fifth one. So we already decreased our dimension from the 10 to maybe 3 or 4. Yeah, and this is how PCA does the dimension reduction. And if we assign our data points to 2 groups, so here I'm assigning the ones that can run 100 meters less than or greater than 11 seconds into the fast and low. We can see, like, we can quickly do a plot on the first PC and second PC, and we can see there is already a separation between the fast and slow. So the fast is on the left-hand side and the slow is on the right-hand side. So this is a very preliminary clustering method. So you're only based on the first 2 PC to see whether there is a clustering within like the categories that you assigned. And there are some more function that you can use to get some more information. So first one is the PCA result, which is a list that holds the mix of data types. You can access individual list elements with the $sign, with something like this. And if you want to know more of what is contained in this PCA result, you can just Google the PCA result. You can see all these documents. And there are a lot of our functions that use list to return multiple things. So for all of these objects, we just use the $sign to get the individual list elements out. And actually, there are 2 ways of doing the PCA. The first one is the PR cop, and there's another function is the PRI cop. So this 2 uses different method to do the PCA. One of them using the eigenvalue eigenvector. The other one uses the singular decomposition. So if you want to know more of it, you can just Google them. There's a pretty good document saying that describing the difference between them. And I'm not going to go really in detail for this one. Yeah, so the PC, so there can be as many as the PCs as your original variables. Each of the PCs is going to be a linear combination of your original variables, and the PCs among the PCs, they're all orthogonal to each other, so they're uncorrelated.